have a stellar lineup of physicists interested in the problem of consciousness this morning. And the first speaker is Lucien Hardy from the Perimeter Institute in Waterloo, Canada. Ontario, Canada. He is known for his work in the foundations of quantum mechanics, quantum gravity. He was at Oxford originally. And it's a great pleasure to introduce him to speak about proposal to use humans to switch the settings in a Bell experiment. Please welcome Lucien Hardy.
Okay, thank you. So I'm going to talk about a proposal to use humans to switch the settings in a Bell experiment. And so I'll explain why this might be interesting, and then I'll talk about an actual experiment that we've just started doing. So first of all, I want to talk about, just take a step back and talk about consciousness and Turing tests. So this is a sort of physicist's take on really more philosophical issues. So it's suitably simplified. Oh, I'm not going to restart my computer. It's suitably simplified so that a physicist can understand these ideas. If you look at consciousness, there are three basic types of ontological account for consciousness. And I put them in this table here. There are those accounts that have only matter, and then those that have something added, some mind added. And then there are also accounts that have no fundamental property corresponding to consciousness, and there are accounts that have some extra stuff, some extra fundamental property added. So the first one is sort of just materialism, straightforward materialism. And this would be something like the standard model of elementary physics. So it doesn't have to be this, but something where you have some basic physics, and there's nothing in that fundamental physics that pertains to consciousness. So the big problem facing this type of approach to understanding consciousness is the hard problem David Chalmers has talked about to overcome the hard problem of consciousness. On the other hand, it's not inconceivable that something could be done here. The second sort of approach is where you still have only matter, but you also have some attribute. That matter has some extra attribute which corresponds in some fundamental way to consciousness. So you can think of it like this. So you have the world. So this is just a small part of the world shown in the picture. And then you have a kind of glitter corresponding to this extra property of consciousness. The whole universe has this extra sort of sparkle, so that even the smallest atoms have this attribute of consciousness. And perhaps in humans it sort of coalesces in some more dramatic way. And then the last of these main ontological types of account would be mind-matter duality. This is the idea that you have, it goes back to this man, René Descartes, and it's the idea that you have, in addition to the brain, there's also some sort of non-physical, non-material mind, and that is in some way responsible for us being conscious. There's a picture here which is meant to illustrate those ideas, although I don't understand how. And this is the approach to consciousness I'm going to be interested in experimentally investigating in this talk. Okay, so first of all, here's an argument against epiphenomenalism. So epiphenomenalism is the idea that you have, say, dualism, where you have this mind, there's a worry that the mind will just sort of sit above the material world and not interact with it, just merely observe it in a passive way. So it does the job of accounting for consciousness, but it's not active in the physical world. And here's an argument against that sort of possibility. This comes from a book by Ewan Squires called Consciousness in the Physical World. Ewan Squires, incidentally, is a physicist, and he was my PhD supervisor. So the argument is, well, the word consciousness appears in the dictionary in black ink, and sure enough, there it is in the dictionary. And so the ink atoms that ended up in that arrangement must have been influenced, presumably indirectly, by whatever it is in the ontology which is responsible for consciousness. You know, I think to myself, I'm consciousness, you know, and lots of other people think that, and eventually a little pattern of black ink atoms end up in a dictionary referring to that property. So it seems that epiphenomenalism isn't really a viable option, and this observation, this is really an experiment. You look in a dictionary and you see if the word conscious is there, and if it is, you've disproven epiphenomenalism. So I called my wife yesterday and asked her to look in a dictionary and then take a photograph of the dictionary for me, just so I could use the photograph. This is just a scan from a computer. I thought it'd be more powerful if I took a photograph. So I asked her to look in a dictionary, and the dictionary we had to hand was the Scrabble Players Dictionary. And so there it is. And you'll see it goes from conquien to consent, and the word consciousness is missing. So this is proof that Scrabble players are zombies. You may ask what we were doing having a Scrabble dictionary in our house. So since the word consciousness does appear in good dictionaries, we conclude that the behavior of matter can be affected, or must be affected really, by the ontological elements that are responsible for consciousness. So from the Cartesian Duelist point of view, that's the point of view I'm most interested in this talk, we can tell a story in which the mind acts on the brain, you know, acts on atoms and molecules inside the brain, and thereby imparts information into the physical world. And somewhere down the line, this leads to a certain configuration of ink atoms in the dictionary. So for this to work, it would have to be the case that atoms inside the brain violate the laws of physics. So we could imagine looking for that. So we could take a very powerful magnifying glass and look inside the brain at individual atoms and try to see them violating the laws of physics. Well, that's a very difficult experiment to do, not least because the brain is a very messy environment. How would you ever investigate this kind of question? So one person who thought about this and came up with a sort of an idea for a cleaner sort of experiment is this man here, Alan Turing. And of course, he believed, it seems, that really there was no extra mind, that you could give a fully material account of matter. And to try and push that point of view, he came up with the Turing Test, the imitation game, as it's also called, also the name of a blockbuster film. So the Turing Test, I think everyone here probably knows that. You have someone interrogating, there's a screen, there's a computer interface, and the interrogator doesn't know if there's a human on the other side or an artificial intelligence system, some computer program. And so they ask questions and try to establish which is which. And the basic idea here is that you take either a human or something that's imitating a human in this context, and you put them in a sort of figurative box, and then you only allow information, classical information, to pass in and out of that box. So you can sort of think about this general class of Turing-type tests. So this is where you put one or maybe more people inside boxes. So these boxes look a little bit uncomfortable. They were the best ones I could find on a Google image search. But don't forget, these are just figurative boxes. And then so either we have people inside these boxes or we have some sort of AI devices. And then we look at the information coming in and out, and we try to establish whether there is mind-matter duality or not. Okay, so that is so this is a more general notion of Turing-type tests. So not just the simple imitation game test that everyone knows, but this is a more general notion of Turing-type tests. Okay. So now let me talk about this is a different world, quantum entanglement and Bell-type tests. This is a very big subject, and people who work in this, know it well. I'm not going to go into great details. I'll just give you the salient features. A Bell-type experiment. So this was invented by a man called John Stuart Bell from Northern Ireland. In 1964, he wrote this paper demonstrating the things that I'm talking about in this slide. So the idea is you have a source that emits pairs of particles. Those particles are entangled, so they've interacted in some quantum fashion. They separate, and then at each of the two ends, you make a measurement. So the measurement has different settings, usually just one of two settings. So at end A, you have setting A, and that can take one of two values. And at end B, you have setting B, and that can take one of two values. And then according to that setting, that determines the measurement you make, and then you have an outcome for that measurement. And then you look at correlations, and you can define a certain correlation function pertaining to this experiment. So I won't write down what the correlation function is because it won't edify you particularly. But you can show that if you assume locality, so if the outcome at end B does not depend on the setting A, so if the outcome at one end doesn't depend on the setting at the other, likewise, the outcome at end A doesn't depend on the setting B, then you can show that this particular correlation function is less than or equal to 2. Okay. But then quantum theory predicts that the correlation function has the value 2.8. So it seems that in quantum theory, you violate this locality property. One end seems to know what the other end, what the setting at the other end is. So I should say, this doesn't allow you to send signals, but it is something that's inferred from the statistics. Well, let's talk a bit about these locality assumptions. We want to be sure that the outcome at end B doesn't depend on end A. Well, one way to do that is to switch the setting at end A, and to do it so that there's no time for information about the new setting to reach end B. So you can see I've drawn the switch happens, and then information about the new setting spreads out at the speed of light, and you want to do the experiment so there's a switch at both ends, and there's no time for information about the new setting of the switch to reach the other end. So in experiments to test bells, these Bell inequalities I talked about on the previous slide, this is what you want to achieve. You want to switch the setting at each end so there's no time for information about the new value of the setting to reach the other end. Okay. Now, in the actual experiments that have been performed, this switching is usually done by a random number generator. So you have some device that spits out, random numbers, 0 or 1, and then according to that number, you choose the setting. There's a problem there. What if this random number generator is really a deterministic machine? Like, it might look random to you, but there could be some hidden state of the machine. In quantum foundations, we usually call those hidden variables that can be used to predict the future state of the machine. And any machine you build, you can never be certain, even if it looks perfectly random, that it's not got some hidden state that is actually deterministic. Well, if that's the case, then the earlier hidden state could be broadcast to reach the other end in time. And so now it's possible for information about the setting to already be at NB at the pertinent time. So if you have this concern about random number generators, then there's actually nothing you can do with random number generators to impose these locality conditions. You can never solve that problem. So the idea is to use humans to switch the settings. If the interventions of mind on matter, this is what I was talking about in the first part of the talk, if we have some sort of mind-matter duality, if they're the kind of things that cannot be anticipated by the laws at the physical level, and if furthermore those physical laws are actually truly local, then the locality condition can be imposed in a Bell experiment by using humans. So the idea is the human, makes a choice, setting between the two values of the setting, and then presses one of two buttons. Then information about that choice spreads out at the speed of light, and you do the same thing at the other end. If you get your timing correct, then you can be sure that that the locality conditions are implemented. There's no possibility of a signal about the setting at one end reaching the other end. So far, no experiments have been done with humans. It's a funny thing in physics. We often talk, figuratively about, doing this or doing that. But we don't really mean that we do this or we do that. We just mean that, this is some part of the setup. And so far, nobody's actually done an experiment where we've actually put humans in this situation. And the reason for that is it's actually very difficult. I'll talk in the last part of the talk about actually how to do this experiment. So you can see here we have something like a Turing type test, the sort of thing I was talking about earlier. We could do an experiment either with humans at each end or with some sort of artificial devices. Here, AI could stand for artificial interventions. So this would be something like a random number generator or any kind of machine you wanted to test in this context. So this is indeed a Turing type test. So in these boxes you have either people or you have these AI devices, such as random number generators. What's nice about this test is that it's more objective. It doesn't depend on human judgment. So in the imitation game of Turing, the interrogators have to use their judgment. Do they feel like the person, like it's a person on the other side of the screen, or is it a computer? And this is a very subjective judgment. Here, it's not subjective. You do an experiment, you measure a correlation. Now, if the correlation function goes down, decreases, so it goes down to 2 or lower, when you have humans, then you'll be seeing something very significant. You'll be seeing, the fact that you've now finally imposed the locality conditions, and you're seeing that nature is really local. Of course, I should say this is a sort of long shot. This is an idea, an experiment that should be done, but it's not. Most people, I think, don't believe this is really going to turn out this way. But it's something we can think about. Okay, so here's the proposed experiment. Well, first of all, we need to find a way to get humans to change the settings, and there's sort of a problem here. You could imagine taking, a human. You could take humans who are, by their own account, very smart, and you could have them press one of two buttons. The problem with this approach, well, there's an obvious problem in this picture, but the other problem with this approach, so far as the experiment is concerned, is that you can predict from EEG signals 1/10 of a second earlier than when they press the button what the choice will be. And that's sort of not surprising because it takes a little while for the signals to travel down the arm and then for the muscles to react. This is mechanical time we're talking about. And in 1/10 of a second, a light signal could carry information about the actual setting so that it's several times the radius of the Earth away. So that's a very big distance. So to do a Bell experiment where you have people doing this, you'd have to have an experiment over several times the radius of the Earth. That's a very difficult experiment to do. First of all, you've got to get people in that distant location, and you also have to share entanglement over that great distance. So instead, we propose to use EEG signals directly. So electrical signals travel through the brain at near light speed, so very little delay is incurred. So if you imagine, in this idea that the mind makes a choice, the brain reacts to that choice, you get the electrical signal out the brain very quickly, and then the setting is switched. You'd want to engage the people doing this experiment in some appropriate sort of choicey behavior, some sort of choicey activity, and it's not clear what that would be. So that's something to think about. So then the second problem is that you need to get your rate up very high. If you have people making a choice, you want to have a lot of these interventions. So an individual person, you could imagine that they might be able to make 10 choices per second. That sounds just about feasible. So then if you have a lot of people, so I'm suggesting that you have 100 people at each end of the experiment, and they're wearing, each of them are wearing EEG headsets. It does start to sound a bit crazy, doesn't it? They're all wearing EEG headsets, and then those headsets are Bluetooth enabled, and they transmit the signal to some relay station, which transmits it to the setting, and so then you can do an experiment. And then in the proposal I wrote up in May in 2017, I suggested doing the experiment over a distance of 100 kilometers. That's because there was an experiment, a beautiful experiment done by Zeilinger's group in the Canary Islands, where they transmitted photons over a distance of about that, and they did a Bell experiment. So if we assume we have 100 people at each end, 100 kilometers, and I assume a 10% intervention rate, then we'd expect to see a 1% effect. So the correlation function should go down about 1%, and that's the sort of thing you could just about imagine seeing. But then, well, so I'm going to talk now about some collaboration that's just starting with an experimental group on an actual experiment. And so in July last year, this paper came out. So this is satellite-based entanglement distribution over 1,200 kilometers, which is remarkable. And this is the paper here. So the lead author on the paper is Yuan Yin, and the group leader is the last name on there, Jianwei Plen. I've begun talking to this team. So this is Jianwei Plen at the top, and just on the bottom, second in from the left, is Yuan Yin. Those are the two people I've mainly been talking to. So this is the group that did this remarkable experiment. So how did that work? Well, they had a satellite launched. On this satellite, there's a source of entangled photons, and then those entangled photons are transmitted down to Earth from the satellite, and they can be captured in adjacent towns, and those two towns are 1,200 kilometers away. The satellite goes around the Earth once a day, and so you have a 90-second period every day when you can collect photons and do a Bell-type test. So the idea is that during these 90 seconds, which apparently happens quite late at night, you would get 100 people in each of these two different cities, get them all equipped with their headsets, engage them in some appropriate choicey behavior, and then take the input from those headsets into the Bell experiment and see if quantum theory starts to be violated, if the correlation function goes down and we get something different. So in the case where such an effect was actually there, the prospects for seeing it in this kind of experiment are very good. The switching conditions would be met almost 100% of the time. Of course, it's a very difficult experiment, and also the rate is very low. So during those 90 seconds, you're collecting 1 photon pair per second, so you're only getting about 90 photon pairs. So you have to do it over a number of nights to get good statistics. So that means that every night for a week or something, or maybe a fortnight, you have to bring in 100 people, equip them with headsets and so on. But still, this is just about feasible. And this team in China seem very committed to doing the experiment. So the last question I want to ask is what if? What if, when this experiment was done, we started to see a violation of quantum theory in accord with this Bell inequalities? So the correlation function went down. But that only happened when we had humans instead of artificial devices. So no artificial device was able to replicate this, but humans were. How would we interpret that? Well, first of all, the consequences for quantum foundations would be very significant. In fact, the consequences for physics would be very significant. First of all, it would show that after all, nature was local. I think by now most people in quantum foundations have come to accept quantum non-locality, so that would be a big surprise. Of course, at the time when John Bell published his result in 1964, it was a big surprise to everybody that quantum theory was non-local. So nature would be local, but also it would have this property of superdeterminism. So remember, in order to explain the existing results, you have to imagine that the random number generators are really deterministic and that they have some hidden state which is transmitted to the other end in order to account for the correlations. That seems like a very strong kind of determinism, and in the literature this is usually called superdeterminism. This is not something most people like, and I also don't like this kind of superdeterminism. So this would be very significant for quantum theory, but the significance for quantum theory, for quantum foundations, would be nothing compared with the importance for the study of mind. Because suddenly now we'd have a realization of this kind of Turing test providing evidence for Cartesian duality. So I think it would provide very strong evidence for Cartesian duality, although you can try to think of other explanations. So you could try to provide an entirely materialist account of this kind of result. So you might say, well, you know, for the most part, atoms are completely, when they get together, they're super deterministic. Atoms, particles inside a random number generator are behaving in a super deterministic way. And it's only when you get to sufficiently complicated machines like humans that you would start to see this breakdown of superdeterminism, and you could violate quantum theory in these kinds of experiments. That's a very difficult sort of idea to implement, not least because you'd want these theories to be local, and it's very difficult to imagine these sorts of properties emerging in a sort of a micro-local sort of theory. It's something that's difficult to do. So I think this sort of result would provide very strong evidence for Cartesian duality. One important point to make here is that unlike a lot of the discussion when people talk about consciousness in quantum foundations, here we're not invoking consciousness to solve the measurement problem. There's a history of thinking about mind-matter duality in quantum foundations, people like Wegener and others saying that mind causes the wave function to collapse. There's also something called the many minds interpretation. And then in the Copenhagen interpretation, some people think the Copenhagen interpretation of quantum theory invokes a kind of mind-matter duality. We're not invoking consciousness in that way in this work. It's an entirely here we have an entirely different flavor. It's not about solving the measurement problem. Oh, I should just talk. So I originally put this proposal out in 1989. The idea I had it 30 years ago. And I wrote these papers. Of course, the papers were not accepted for publication. Here's the picture from the paper. You can see you have two people, and you're taking the signal directly from the brain via EEG signals. So it's very satisfying to me that now, 30 years later, we're actually in a position where we can do this experiment. So I'd say 3 things have changed in the last 30 years. Yeah, the third one, of course, is the most important. So attitudes have changed. People are more open to talking about this kind of thing. This conference is some evidence of that. I see the red light is flashing. The experiment is just about feasible now, as I talked about. Back 30 years ago, there was no chance this experiment could be done. And of course, I have tenure. Back then, 30 years ago, I was actually very confident that a positive result would be seen. By now, over the years, sort of age has worn off the rough edges, and I think it's far less likely that we'd get a positive result. I would say the result is something like 1% or 3% that we'd see a positive result. It's very funny to put probabilities on the top of theories. It doesn't make sense, but nevertheless, I think about 3%. Incidentally, the reason for that is I think there's a very high chance that something like mind-matter duality is correct. I'd put that at about 30%, but I find superdeterminism to be quite distasteful. And so for that reason, I'm giving this a very low probability of about 1%. Though many of my colleagues think that is crazy, and they would put the probability much, much lower. Nevertheless, the probability times payoff is very big, and so it's worth doing this kind of experiment. So often people say that Cartesian dualism is not a valid scientific point of view. This experiment shows that we can address the issue of dualism scientifically. So even as a thought experiment, and even if the experiment was done and turned out not to be positive, it's still valuable to have these sorts of experiments to talk about. And then we can ask questions like, how would we interpret this were a positive result seen? So I've talked about using humans, but why not penguins or other animals? Here's a picture of Roger with, so there's a rumor that Roger has a pet penguin. This was on Wikipedia, and Roger was telling me he was very disappointed this was taken off Wikipedia, so I'm hoping to get this rumor going again. So if you can take a photograph of this screen and tweet it, then maybe we can get Wikipedia back on with this story. So yeah, we could imagine not just humans, but not super intelligent humans like in this example. But we could also maybe penguins or mice, or would also we could do the experiment. And I'll leave it at that. Thank you.
Thank you. Very, very interesting. Can we switch over computers, and we'll have time for 1 or 2 questions for Lucien? Yeah.
Yes. In general, have people really gone back and questioned some basic assumptions that superluminality is definitely off the table? I'm aware of G. Spencer Brown's doubt about probability and randomness, and Arthur Kessler's parapsychology experiments also cast doubt on randomness. Have these been looked at very carefully and eliminated as possibilities?
I don't know the work of the people you mentioned. And, in physics,
are you familiar with laws of form, G. Spencer Brown?
Yeah, so in physics, it's always impossible to be completely certain you've eliminated these things. And in fact, actually, Bell's this work of Bell does suggest that there is superluminal transfer of information, right, but you can't use it to send signals. But you can. It does mean you have a stronger correlation than you would expect between distant parties. So people in the community have talked about something they call pseudo-telepathy, which is where systems are, because they're more correlated than they are in classically, if they want to evaluate some function on their separate inputs, they don't have to communicate with each other as much as they would without quantum entanglement. So this is an established result in quantum information. But yeah, these questions are always open, of course, in physics, and I don't know to what extent. I mean, so far nobody has seen in an experiment of the sort of experiments I'm talking about, no one has actually seen superluminal transfer of information, where it's verified that you do something here, and you get a result of that you can measure at a distance. But there is this sort of more subtle sort of correlation that we see in Bell's theorem.
Okay, thank you.
We're going to have to cut it off there so we can leave time at the end for all three panelists. Let's give a big round of applause to Lucien for a fascinating talk. Thank you very much. Our next speaker, it's a great pleasure to introduce Robert Alfano. He's a professor in physics at the CUNY Institute in New York, at CCNY, and he'll speak about photon quasiparticles probe quantum processes in the brain. Bob.
Thank you very much. It's a pleasure being here, my first time in Arizona, and I thank Stu for inviting me. Today I'm going to be talking about quasiparticles, really photon quasiparticles, and I want to talk about how there are different amazing features of photons, and I hope it's going to be a change of direction from the previous talks given at this conference. It's going to talk about how photons can be classically entangled and quantum entangled, depending if it's local or non-local. And we're going to do some experiments. That's what I do, an experimentalist. I'm going to do some experiments to show both this classical entanglement and this quantum entanglement in brain tissue. We have done it in different types of media. So the title of my talk is Quasiparticles Probe Quantum of Processes. Stu introduced me, he wanted to know about quantum processes in the brain. So there's a lot of stuff going on in the brain, which is quantum. And before I do that, we have to, how do I change this? Up top, right? Oh, there we go, okay. So the motivation of this talk is photon transport in the brain. And we're going to look at all the optical processes that occur in the brain and to see that these are based on quantum mechanics. And we're going to be talking about, like I said, the classical and the quantum of processes that give rise to possibly diagnostic information that occurs in the brain. So the focus of this talk is going to be on my discussion first on what is a quasiparticle. I don't know how many people in this audience understands what quasiparticles are, but they live in the brain. They live in any material. And I'm going to introduce some new quasiparticles that are based on quantum and classical entanglement. So in this talk, I'm going to show you the basic properties of light that most of you know. But I'm going to make sure you know it after this talk. And I'm going to discuss various processes that occur where light interacts with the media. In this case, it's going to be the brain. And we're going to be talking about fluorescence from the key molecules in the brain and finding out what's going on in, for example, Alzheimer tissue versus normal tissue of a mouse. And we're going to find some interesting properties that we didn't expect. And we had to prove what causes this enhancement of the fluorescence in an AD tissue, that's Alzheimer's tissue. So we did a series of experiments to prove what the problems are and what's the underlying physics. And then I'm going to be talking about the transmission of polarized spin and orbital angular momentum of photons in the brain. And also tell the difference between classical and quantum entangled photons transmitted through a brain to see if we get any information about quantum effects in the brain. So first of all, we have to talk about the salient properties of light. And photons are amazing. Sometimes they are waves, sometimes they are particles, and they have these properties that are listed here. The first one is wavelength, color. Photons have color. And on the side of it is a spectrum. I don't know if this works. Oh yeah. There's a spectrum here that goes from 400 to 800 nanometers, but it spans further than that. This is called the supercontinuum of a femtosecond pulse coming out of a laser. It has time. Photons have time. They can be very short, and these could be picoseconds, femtoseconds. They have polarization. You could play with the polarization, linear polarized, circular polarized, and sometimes the light is coherent, like this laser pointer. They're all in step. A very interesting characteristic of the photon, it's its wavefront. You have a beam coming out, like this beam is Gaussian of the laser pointer. It's just a bell-shaped curve. Nothing to do with Bell inequality, but it's bell-shaped. But the wavefront, normally we know, is a plane wave traveling in a plane, but it also can have this helical form, which is called optical vortices. It looks like a donut. So this beam has come on the horizon in the last 15 years. It can have angular momentum, orbital angular momentum. Besides being circular polarized, you can have orbital angular momentum. And the trick is you send polarized light, plane polarized light, hitting a spatial light modulator or a spiral plate. It comes out twisted. Again, I shoot it. I'm not very good at this. Okay, I get this. Okay, these are basic equations you all know. That E equals h nu, that's from Planck and Einstein, and C equals lambda nu, that's momentum. And you then have the, oh God damn it. I hate this thing. Keyboard, that's a good idea, thank you. Whoever said thank you. This keyboard is not my computer. I can see up, I see up and down. Good. Okay. Green light, everybody knows a green light, the wavelength is 500 nanometers. The basic unit's light, nanometers. That's the wavelength. Time, picosecond, femtosecond. These are characteristic times of the photons. Okay. Now we're going to talk about the classical and quantum photons. Photons, low number, photon number are usually single photons. They give quantum effects. Photons at high numbers give you classical wave effects. Now we're going to be talking about this new light, which is called vector vortex beams, which have both spatial and temporal properties. And we're going to use that to see about how we could talk about classical entanglement of photons, which is local, versus the quantum aspect, which is non-local, meaning you have two particles that you're going to interact with. But before we do that, we must talk about these quasiparticles that I'm talking about. No? Okay. The overview of a quasiparticle. Quasiparticles exist in materials. They can consist of phonons, excitons, plasmons, magnons, and this polariton. So when a light beam enters a material, such as a Lorentz dipole media, which has a resonance, it changes its speed, and it becomes dressed. It becomes C over N, and it comes through, and it comes out. So this is a standard type of problem where the medium acts to disturb the light. Either the light is going to transport through and see what the medium is all about, or get excited. And the most important thing about these Lorentz dipole, they have dispersion curves. Now, a photon, which is the lower portion of the curve, lower left, is a straight line. And these dispersion curves of different excitations that live in a material, such as phonons, plasmons, and magnons, these are excitations that live in a material. You could have excitons, but they could couple with the light, and you get these polaritons, which are modes which are coupled to the photon. So you have a coupled photon elementary excitation in a material. And there are two regimes. If you look at the far, I hate to do this. Shit. Yeah, okay. this coupling here occurs between the photon and the resonance in the material. And the lower frequency is called Brillouin precursors, and the upper one is called Sommerfeld precursors. And these are the type of waves that travel in a material. For example, if you send a light pulse from the left going in at a certain frequency, it should be omega 0 is omega C, going into this Lorentz dipole that's in the brain or in the semiconductor or tissue, and the different waves come out, different speeds, because they travel with the phase velocities and the group velocities in the material. The higher frequency wave, which is the J1 SP, is essentially the Sommerfeld precursor. It travels C over the index of refraction, high frequency, followed by the Brillouin, which is a low frequency excitation, and then the signal. So this is the type of, and this has been discovered by Brillouin, not discovered, proposed or theorized by Brillouin and Sommerfeld in 1914. And to date, only one experiment has been shown to show this phenomena in these materials. And we're looking at that into various microscale particles. And the characteristics of these special waves travel as 1 over z. It's an algebraic expression, not an exponential. So due to our work on introducing these classical entangled photons and these quantum entangled photons, I'm going to propose two particles, excitations, that occur in the brain that talks about this orchestra that Giuseppe talked about last night, about this orchestra in the brain, which has got to do a dipole type of effect. And these two particles, one is called QANs for quantum particle, quasiparticle, and CON, which is a classical particle. So let's go now on to what happens to the light as it goes into this material. Be it a brain, be it a semiconductor, a liquid, you get these quantum effects. When the light gets, the one on the right here, you got the fluorescence that occurs in a material. And obviously fluorescence is obvious that fluorescence occurs in the brain if you excite it. And then there is the 1 photon process, then you get the 2 photon process, meaning 2 photons are needed to excite the material, and this material then emits, and it's called 2 photon or 3 photon fluorescence. If you don't reach the first excited state and you look at the vibrational states, those are the Raman processes. So these light interacting with matter, such as the brain, has quantum effects. So in a sense, there are quantum mechanical things going on in the brain. But photons are very amazing in the fact that you could have special functions that solve the Maxwell's equations that in different coordinate systems. And one of the important coordinates is a cylindrical coordinate system, where you get these vortex beams, these donuts I talked about. And some class of donut beams, or vortex beams, can be considered classically entangled, non-separable. They can't be separated. So this radially polarized beam, which is a mixture of both orbital angular momentum and right-hand circular, cannot be distinguished from right-handed circular polarized light and angular momentum L. And there's also azimuthal. The pure states, such as circular polarized light, are not entangled locally, but these two particularly are entangled locally. And you can do experiments with pure states, such as circular polarized light, versus radially and azimuthal polarized. Next slide I hope next slide is got to do with what it looks like. These two beams are locally entangled. So when the light goes through a brain tissue and transmits through a brain tissue, the thing is locally entangled, and they go through the maze of the brain, which has got all these neuron trees and complicated structures in the brain. And obviously, the pathway of the photon going in these things are different. So this is an example of this vector vortex. It's so the azimuthal part is this 1 AP. I use this Dirac notation, such like quantum mechanics, but it's just the field. And then you got the donut plus the polarization. And these two mixture states are entangled in the radially polarized state. The circular polarized state over here on the upper right is pure state, and it's not entangled. So one of the experiments we did is to just do the simple excite the material with light and look at what happens to a brain tissue that is Alzheimer versus normal, and to see what the emission looks like, what effects are occurring in the brain, and to see indeed if there's a difference. It turns out, by surprise, the emission from an Alzheimer tissue is larger than the normal tissue. And usually in semiconductors or in lasers, it's the opposite. If you have defects in the material, the yield is less. In this case, having a defect in the Alzheimer tissue, that's supposed to be defect, emission is more. So the question was, why is it more? Is it due to more molecules in the tissue, or due to a more fancier term, non-radiative? Usually in laser materials, the non-radiative is very small, and because you want to have radiation. So in this tissue, Alzheimer became more intense. And the experiment then to see why is it more molecules, or has it got to do with the non-radiative, is use fluorescent lifetimes. So we use 2-photon and 3-photon excitation using a time-resolved instrument called a street camera to measure the fluorescence decay on a picosecond time scale. So over 1,000 picoseconds, we found that the lifetime in AD is longer. Instead of being shorter, it's longer, which then points to the fact that the non-radiative process gave us more emission. So that was a very big discovery. It seems as though AD molecules are freer to move around in an Alzheimer tissue. And to go one step further, to see if there's a rotational motion of tryptophan, for example. This is tryptophan on the right side. It's got 3 parts to it. It's got a ring, a midsection, and a terminal end, and each one has a different vibrational frequency. So tryptophan in the protein is sitting there. Is it coupled in the Alzheimer more or less than if it was in the normal tissue? So therefore, we looked at these 3 vibrational modes, and it turns out tryptophan is freer in the AD because the frequency we measured of these different bonds on the lower part of the screen here, the frequency is more like free tryptophan. So it all points together that probing the quantum effects in the brain by different spectroscopies, we're able to handle what's going on in the tissue. Now, switching to the key part of this talk, believe it or not, is the fact of looking at classical entanglement, which doesn't make sense to most people, and most of the people don't like the idea that we're talking about classical entanglement. But if you look at the radial polarized equation, which is in this Dirac notation, it's a mixture of the orbital angular momentum, that's the donut part, and its polarization. And it's a mixture of 2 types. And so radial polarized is classically entangled. Basically, it looks more or less like the first Bell equation that was put on. They didn't put the equations down, but mentioned it in the previous talk. And so the experiment we did, both for classical entanglement and for quantum entanglement, which was the end of the talk, good, is shown in this slide here. First, the classical. We use this vector vortex beam. It's called a Laguerre-Gaussian. So you solve the wave equation in cylindrical coordinates, you get the Laguerre polynomials, which is this donut modes, different modes. If you pick the lowest mode, it's got a 1 ring. If you have L equal to 2 orders of angular momentum, 2 twists per wavelength, you get L equal to 2. So when you send these different waves, light pulses, into the mouse tissue, different points of the brain, we essentially measured if there's anything that affects the type of polarization we put in to see if there's any chirality, twist when you do angular momentum, because the beam is really twisting as it goes through. So if you have L equal to 1, there's 1 twist. If you have L equal to 2, you get 2 twists. And you also can have spin polarization. So we didn't change the spin polarization that much. But the idea is we measured the transmission through a brain tissue of a thin tissue and a thick tissue. This was 120 micron tissue. Just this, so it's one beam. It means local beam, no two beams, one beam. And we wanted to see what happens when we change the orbital angular momentum. Again, orbital angular momentum means the number of twists per wavelength. And so the beam is twisting like the macaroni rotelli. You remember rotelli? It's that twisted macaroni? That's what a twisted vortex beam looks like. But it's not the macaroni traveling here. So we measured the transmission with linear polarized, circular polarized, and with the special beam of radially polarized. And because radially polarized is the only one that is a mixed state, and it has this entanglement between the orbital and the thing. And we found that there's differences in the transmission. Too early to say how much we learned from this, but we definitely showed that linear polarized doesn't really affect it at all by this twisted light, because it's linear polarized. And the other one, chirality, measures the type of twists and so forth. So now let me switch gears a little bit and talk about quantum entanglement, which everybody knows about. Now, quantum entanglement means the photons, in this case, not electrons, the photons are non-separable, they're non-local, they're inter-entangled, a low photon number, single photons. The entanglement refers to, as I read here, a non-classical correlation between two spatially photons or particles. Here you have the mother photon splitting into two daughters. These are twin photons, twin daughters, that if you touch one of the photons, the other photon, number two, is affected. So this is a non-locality, is the key of quantum entanglement. So we have to do an experiment with two photons, not like the simple experiment, but just doing one photon going into a tissue and measure the entanglement of that classical beam. This shows you a picture of what a pure state looks like, which is not entangled. That's the top one, which is right-handed circularly polarized with different orbital angular momentum, L. So you get, it's a vector multiplication of the phase of the angular momentum plus the twists, how many twists you got. This is the polarization. First part is the polarization. Second part is the number of twists. Well, now below you can see that the more complicated right-handed and orbital angular momentum plus left-handed, you don't know which one you have. That's more or less the entangled beam. So in essence, you could make these two photons obey the Bell states. You could pick one of these four, and we picked the top one, psi plus, which is made up of linear polarization H1 on one photon, H2 on the second one, V1 means the vertical, plus multiplied by it. This is the common state called phi plus in the general entanglement of Bell's inequality. But this is also made into photons. So we have these wave functions, essentially, that we talked about, and we could then have these photons either in a pure state or a mixed state. These are the mixed states. And most mixed states are not entangled. These happen to be entangled. And now, the wave function is very hard to tell. You do have an entangled beam. It's very hard to see. How do you determine that your beam is entangled? So there's, what these people use, or us, we use, is mixed states are described by this density matrix. There's an operator. Rho is psi times psi reversed. And this is you want to send in H1 means horizontal, these two photons. And this is the Rho matrix describing that. H1 and H2, V2 is this one, and so forth, these Rho matrices. And you form from these states the density matrix. This wave function is really psi plus. It's going to do with H1, H2, sum V1. So you don't know what you have until you measure it. And this is the row matrix that talks about it. So this state we talked about here is a mixture. Half the time it's in H1, H2, or it's in the other half of the time. You don't know until you measure one of them. So the two states that we have, this state, are distinguished only by the density matrix. You need a density matrix, and you form this density matrix, phi plus, as the multiplication of the psi with itself in reversed order, and then you get the density matrix, and you see you have off-diagonal terms on the upper corners. And this is an indication that this is the perfect entangled beam. And when you measure something, you measure it relative to this as the standard. And a totally mixed state, which is just the sum, not the multiplication, the sum of H, you could tell the difference, and therefore you don't have these off-diagonal of the density matrix. So this mixed state is not of totally mixed, random, not correlated, and not entangled. The two different, when you measure the matrix by these mixtures, you can measure the entropy, which is a standard by Bose. When you measure the density matrix, you get the entropy, how mixed it is. The concurrence, fancy word, meaning tangle, the C squared. And you measure this, if you have this wave function, which is made up of all these three different polarization measurements, alpha, beta, gamma, delta, and you find out if your tangle is 1 means totally entangled, 0 means just uncorrelated. And this Werner state down the bottom is a mixture, because you don't have usually your photons coming through, it's not a pure beam, it's got a mixture of mixed and entangled. And you get this standard curve, this tangle curve, and it tells you a perfectly entangled beam, p equal 1, is the tangle is 1, while the entropy is 0, and when it's totally random, 0 tangle, and total entropy. And this one is the example of a perfect density matrix. And how do you plot? You usually plot this in a three-dimensional graph, which shows the different polarizations, the four corners. If you have four corners in this diagram, that tells you you're perfectly entangled. So you measure these polarizations, the intensity of these correlated beams, and you find out that you have entanglement or not. So how you generate this, you go into it, you have spontaneous generation down conversion, of phase 2 phase matching, and you use these two dots, which are circled, as the beams coming out from your crystal as the entangled beam. So in the experiment that we did, this is the beam coming out at high intensity. This is the tissue. We put it somewhere in the beam over here. On the top part, there's a sample, and the very weak beam comes out from the diode laser 409, 401, goes BBO, and we generate the same entangled state, H1, H2, times V1, V2, the two beams. We don't know which beam we have coming out of this beam until we focus it into one photodetector and the other one, and if you do this without the tissue, you get the pure state, the one that shows the 4 ones in the corners. But when you add the tissue, when you add this tissue of the brain, the question, the photons become mixed, you would think. You would think that it would become distorted, decorrelated due to the scattering in the brain, but it turns out this is not the case. This shows the example of a healthy brain and a not healthy brain, and you can see the density matrix graph, if you like, is shown here for the healthy brain, while the one, you can even just look at it differently, more scattering, and you get less in a diseased brain. And we did, this paper up here, this paper was published last year, almost 2 years now. No, it's 1.5 years. That was in scientific reports by Dr. Shi. I had to mention that I'm collaborating. This talk is based on the work done with Dr. Shi and Alves from Colgate. And anyway, when you measure these samples, different types in the cortex, and the white matter, and and then also a kidney, you get this curve which shows there's a variation with tangle, but it says there's still the beam remains entangled, going into the brain of different thickness. And we did it also with glioblastoma, and we're still working on that, finding out how we could tell the difference. And we have learned that now we have to focus very hard into the tissue to try to get at these microtubulars that Stewart and Penrose have proposed that has the memory in the brain. So it may be resulting of consciousness. So in conclusion, I think I showed you that quantum processes do occur in the brain in various steps, because when you do all these optical experiments, it's all based on quantum. And we could then, from the work we've done so far, there is very little correlation between thickness. Thickness is still, even though you go from what they call the ballistic regime, when light goes straight through, to a diffuse regime, the thick and thin of photons traveling in scattering media, there's still a correlation of entanglement. And the idea is the pathways, we're trying to find the special pathways, if there is some special pathways, in the maze in the brain. So we have to do more experiments at different spatial locations. Do I have anything else? No, that's it.
Thank you, Bob. Maybe a couple questions while we set up for the third talk. Do you think in the first experiment the increased emission was due to structures like microtubules, for example, disassembling, which they do in Alzheimer's, so the tryptophan would be
freer?
That's
right.
Okay.
That's right. And we have to do, the problem is it's very difficult to get funding for these experiments. This was done on the backs of other grants. So it's very interesting that people still don't believe there are quantum effects in the brain and things like that.
We're trying to change that.
Yeah,
Okay,
right.
Thank you very much.
That's it.
And we'll have time at the end, I think, for panel.
Okay.
You all?
Okay.
Question here?
Keep this one. Take it.
Oh, wait, one question.
You got time for a question? All right. So I like what you've presented here. It's very interesting. I'm a physicist myself. And what do you see as the consequences or the implications of this work of the physics of quantum entanglement for medicine?
I think it opens the door to a new era in investigating using all these laser type of techniques to try to unravel the brain. And it really has been an onslaught of multiphotons. Every biology department has multiphotons looking at imaging of what's happening in the brain. They're not looking at what's the molecular process, just the imaging of it. And there are two types of imaging used for the brain right now. Like I said, 2 photon, and it looks at the electronic states, which I showed in the first slide. You look at the electronic states that exist in the brain from the molecules that are there. The newer version, the stimulated Raman, which is the lower portion of the curve, stimulated Raman gives you the vibrational problems of the brain or the structures. So you can look at what's happening in the diseased versus non-diseased. You could excite it and see what happens to the imaging that is occurring on the vibrational structures from lipids and proteins. So I think there's going to be a lot more done. That's why I hope to introduce the people here to the optics, in a sense, and the different techniques that are available. I didn't touch on ultra-fast, which my laboratory is really focused on, using these clocks. That's another era of how you could see what's going on dynamically in the brain.
Thank you.
Okay.
Let's give Bob a round of applause. That's really Third speaker, Christoph Simon, University of Calgary, Canada. Could photons and entanglement play a role in the brain? Seems to be a theme here. Christoph.
Right. So as Stuart, I'm very excited to be here. It's a very interesting conference in a really great location. So as Stuart said, oops. No. Okay. I'm from the University of Calgary. You see a photo. So it's a beautiful place, but it's still winter there right now. So it's a nice change to be here. And yeah, you heard the question. Could photons and entanglement play a role in the brain? That is the big question. So why should we look for unconventional sort of physical mechanisms in the brain at all? You know, there's of course a lot that's understood, right? Everybody agrees that there's electrical signals and chemical processes playing a role, so why wonder about photons and entanglement? So I think that even most mainstream neuroscientists would agree that there's still a lot of open questions, right? So memory is not really fully understood. It's not really understood how anesthesia works. And of course, the really big one is that consciousness is not understood. So like, why does it feel like anything to be us? We really don't know yet. So, and this is of course the mind-matter problem that has occupied philosophers for millennia and scientists certainly for centuries. That there is an added urgency now because we are starting to make these machines that can seem very intelligent, certainly, and where soon we'll really be wondering, you know, we'll see Sophia, maybe Sophia, the robot, is not conscious yet, you know, but soon we'll have these machines where we might really wonder if they are, right? So how, it's important to understand what underlies this. So maybe modern physics can help. That's the hope. So how? And why quantum physics specifically? There's really different ways that one can come at this and different motivations one can have. And I would like to list 4 here that seem meaningful to me. So one is that it seems in quantum physics it may not be totally unavoidable to talk about consciousness, but it's certainly almost unavoidable. And Lucien Hardy before alluded to these questions. You know, like even in the mainstream interpretation, the Copenhagen interpretation, the observer, the act of observation plays a really important role. And one can try to sort of talk oneself out of that, but it's not so easy. And I'll have a slide dedicated to that very soon. Then there's the holistic character of quantum entanglement that might solve the binding problem, and I'll say more about that too in a couple of slides. Then now, of course, we have quantum computing now, right? This is becoming an industry, and so it's apparently useful. And one might wonder whether nature could have discovered it first. That would be the third. And then finally, but related to that, we really have seen tremendous progress in technology, in quantum technology over the last maybe 2 decades. And that just makes it more believable that nature could also have done something like this, because we are starting to understand, you know, what's possible. So, and a lot more is possible than people would have guessed a few decades ago. Okay, so here's my one of the more controversial slides, I think. So consciousness is hard to completely avoid in quantum physics. In the Copenhagen interpretation, sort of mainstream textbook quantum physics, we talk about the collapse of the wave function that happens when the system is observed. Okay, so that's already, it seems, certainly at face value, you know, you would say the observer plays a key role. That prompted some of the founders of quantum physics to wonder about this, and Wigner was a very prominent one, Eugene Wigner. You know, is it consciousness that causes this collapse? You know, does that really happen? Okay, so the question is certainly out there. Then one can take a different point of view on this. One can say, well, maybe really there is no collapse. Maybe the whole universe is a giant entangled state. That is often known as the many worlds interpretation, or there's a version of it that's called many minds that Lucien mentioned. That's detailed in this book by Lockwood. But then even if one does that, again, one has to think about consciousness, because there's the question of, like, what's the basis of consciousness? You know, how can one analyze this why do I see one world? If the whole universe is a giant entangled state, so I have to think about what's the quantum state corresponding to my conscious experience. I can't avoid it, okay? Not this way, at least. And I also have a little paper on that. So, okay, so it's hard to not talk about consciousness when you talk about quantum physics, but there's no consensus on these things, okay? All right. Another, I think, logically distinct argument is this one here. So in classical physics, really nothing stops you. Even if a system is very complex, you can always understand it in terms of the dynamics of its parts, at least in principle. Maybe not in practice, but in principle, you analyze it, you cut it into the smallest pieces, you analyze what each individual piece is doing, you are fine. But this means that the unity of consciousness, the fact that we somehow have a unified experience arising from our very, very complex brains, is very strange. It's very hard to understand from this classical perspective. On the other hand, quantum entanglement is really fundamentally holistic. Okay, and one of the first people to really highlight that was David Bohm, Lucien also mentioned. In quantum entanglement, the state of the whole can be well defined, for example, while the parts of the system are in indeterminate states. So there are strange things like this. And you really have to think of an entangled quantum system as a whole. There's just no avoiding it. In a mathematically precise way. Okay? Related to that is quantum non-locality. So particles can be intimately connected even over long distances. Again, the previous speakers already told you about that. And Bayes' theorem in particular proves that entanglement really is fundamentally different from classical physics. So that gives one hope, maybe, for this question of the unity of consciousness. And to my knowledge, the first person who really expressed that very clearly was Ian Marshall, who I think was a psychiatrist, actually, but with a strong interest in physics. And he wrote this fascinating paper in 1989, where he really already proposed quantum physics as a solution for this binding problem. What kind of physical structure could most plausibly be associated with consciousness? It is argued from the unity and complexity. So both the unity and the complexity together. That's what's hard to understand classically. He says it's argued from the unity and complexity of the states of consciousness that no classical physical system could play the role, and then he proposes Bose-Einstein condensates. Okay. But entanglement in general has these features of unity and complexity at the same time. Okay, that was number 2 of the reasons. So number 3 would be biological quantum computing. So quantum computing uses unique features of quantum physics, in particular, superposition and entanglement, to solve problems that are difficult for classical computers. So if that's good for us, if that's a good technology, maybe it's also good for nature. And one person who has recently been pursuing this idea is Matthew Fisher, who wrote this paper 3 years ago now that was called Quantum Cognition, the Possibility of Processing, and he means quantum processing with nuclear spins in the brain, for example. All right. And at the same time, as I said already, there's really tremendous progress on the technology side. So where maybe 2 decades ago, quantum technology operated only at low temperatures in vacuum. So it seemed very unlikely that something like that could happen in the brain based on the technology of the day. Now this has really changed. Okay, so recently, we are doing quantum things at room temperature, in condensed matter systems, usually with spins, so that's going to be part of my message. Here is a paper called Room Temperature Entanglement between Single Defect Spins in Diamond, for example. Room temperature quantum bit memory exceeding 1 second, again, in a solid with spins. This here is a paper even about spin qubits in liquid at room temperature, the times are not quite as long, but they are also getting longer. So these things are possible somehow. So that's encouraging. Maybe it could really be true. Doesn't mean it is true, but maybe. So this is, it's funny that Lucien had almost the same photo here. So my sort of main job is quantum networks, sort of developing sort of the plan for quantum networks on a large scale, maybe on the global scale. So this is a recent sort of vision paper I wrote in Nature Photonics. This is the launch of this Chinese quantum satellite. I had no idea that Lucien was going to mention that already. So it's possible now to distribute entanglement over hundreds of kilometers, certainly. The goal, though, is to turn this into a real network where you can't just send the photons, but you also have nodes, sort of quantum computers, for example, or other kinds of nodes that can store the entanglement and process it somehow. That would allow applications like secure communication, all kinds of better sensing, telescopes, clocks, things like that. And then in the long run, a real quantum internet, like quantum computers that are connected over long distances, things like that. So my main point here now is that we are working actively on developing components for such networks that could work at room temperature and involving light and spins, typically. Okay, so that's what I do with a lot of my time. These are some recent papers. Okay, and now I'm coming to the brain. Okay, so on the other hand, I learned a few years ago from Jack Tuschinski, who is maybe here, I think, that there seem to be photons in the brain too. So there's not a lot of them, but there do seem to be some. So this is based on the work primarily of Jiapei Dai's group in Wuhan, in China. And what they are doing is they have slices of rat brain, and they look at it in a dark room, basically, with a sensitive photodetector. They do have to add some glutamate, I should say. So they do, it's not, you have to slice of rat brain. I think that the photons are hard to see if they don't add anything, but when they add glutamate, then it really lights up. And you would argue that in a really living tissue, maybe it's more realistic to add a bit of stimulation. So it's based on this. However, people have really seen photons, like weak level photon emission, not just in these particular experiments, but from many kinds of cells. So the area of biophotons, that's a real area. And people have thought about where they might come from too. And it seems that reactive oxygen species are one particularly likely and popular source when people are thinking about these things, because these are like excited molecules. They carry a lot of energy, and some of that energy can be converted into light. So it's not crazy that there could be some photons, okay, in the brain. And I don't need a lot. Right? I'm a quantum guy. I don't need a lot of photons. It doesn't have to come out of your ears. So like a little bit is okay. So the question we asked, so I got excited, when I heard about this, I got very excited. I was like, okay, now I have an entry point into this, fascinating field. Let's think about this more seriously. Could these photons be used for communication? And of course, being a quantum network person, I was immediately interested in that aspect. Could it be quantum communication? That would be really, fascinating. But honestly, even classical communication by light would be quite interesting, right? Even if we discovered just that would be fine. So is that believable? So first of all, let me start with the detectors. Okay, so we started reading, and with like some digging, we found that really there are potential photon detectors in the brain, which is this class of, for example, these are not the only ones, but this is a particularly intriguing class of molecules which are called opsins. So we have a particular kind of opsin in our retina. It's called the rhodopsin. The definition of an opsin, I think, is that it has, so it's a protein, and in the center there's a small molecule that's called the retinol, which is the one that primarily interacts with the light. There's the retinol is a small molecule that has a tail. When a photon hits it, the tail moves. That's called a photoisomerization. And then the movement of that tail is detected. It doesn't just move, it flicks into a different position. Okay? And then that changes the conformation of the protein, and then in our retina, that's translated eventually into a neural signal. So molecules from that same class that have this retinol in the middle, so that are in principle light sensitive, actually have been detected all throughout the body. Okay, so we have them in our brains, we have them in other body parts too. And here is a geneticist, expert, Alice Popejoy, in her recent PhD thesis. This is what she says. Okay, very different community. It remains a mystery what light receptors could possibly be doing in heart muscle, reproductive tissue, and deep in the brain. But the fact is, humans have more non-visual light receptors expressed more ubiquitously throughout the body than visual photopigments. So we have a lot of these things that can detect light everywhere in us, and we don't know why. Okay? And then she goes on, she says, well, it's possible that they are used for other things. Still, the most likely is that somehow they are there to detect light. Okay? So that is somehow encouraging to me. Now, okay, suppose even we have detectors. How could that be useful in the brain? So the brain is of course very, very complex, a very complex structure. There's a lot of neurons. If they are going to communicate, for the signals that we know, they use axons, right? So one neuron will talk to another neuron in a very targeted way. There's a cable that connects them, can branch out and so on, but still, so it's a very organized system in that sense. And the big idea was, so is it imaginable that the same axons could act not only as electrical cables, but also as optical fiber cables? That's what we wanted to know. Okay? There again, I had sort of an exciting few minutes where I was like, okay, once I had the idea, I need to find out the refractive index of an axon. And the idea could have died right there, right, really fast. Because like for sure, for light guidance, you need the refractive index of the thing that guides the light to be higher than that of the surrounding medium. Okay, so this is a basic physics thing. Then you can guide by total internal reflection, which some of you might remember from your physics courses in high school or university. So, and that test, it passes right away. Like it took us a little bit, maybe a couple days to find some information about the refractive indices, but those are fine, okay? And then it turns out, so these are, nothing in the brain is constant, but these are sort of approximate values. So the surrounding medium is basically water with a little bit of stuff in it. So the refractive index is 1.34. And then the axon, a naked, I'll come to the myelin in a moment, but sort of an axon on its own is already much higher, so that's great. 1.38, you can definitely guide. And then many axons have this myelin sheath. So they are wrapped by a sheath. That's important also for the electrical conduction. And that's made by glia cells. And it turns out that that's even higher. The refractive index of that is even higher. So that would be an even better guide, okay? Better guide for light. So then really, so the basic physics is fine, okay? So this can be a fiber cable. Can it be a good fiber cable, or how good can it be? Because of course it doesn't look like a fiber cable that you buy from a cable company, fiber company. So there's a lot of structure and a lot of irregularities and so on. So then the question was, can we, how well can it work, and can we analyze that? And so I'm in a department where there's a lot of optics and photonics people. So I went to see my nanophotonics colleague, Paul Barkley, and said, okay, we want to model an axon. What software should we use? What kind of programs? Like, how do you do this properly? And that's what we did. Okay, so we did a nanophotonic study of our best model of axons. Right. So the thing really that we worried about the most, I think, were the nodes of Ranvier. So we were particularly interested, like I said, in the light guidance in this sheath, actually. But then the sheath, this that I drew in red, is interrupted every few hundred microns in these nodes, where then there's just the axon. The axon goes on, but the myelin sheath is interrupted. And that was a concern, would the light make it through these nodes? So we built a model here with this software that I described. We built a model that we tried to make, pretty realistic, because like here, so the sheath has layers. There's sort of these glia cells, they extrude this sort of a sheet, and then it wraps around, and then these layers have to terminate in these nodes, and like in these termination areas that's in red here, then there's a lot of small structures, microtubules, and so on, and this is not good for us, okay? They might be doing very interesting things, but from the point of view of just light guidance, they are scatterers, and that's not great, okay? They might be sources, that would be super, but if you just want the light to go through, then that's a nuisance. So we tried to model that in a fair and realistic way, and then we propagated the light through theoretically, okay? So this is our calculations. But we concluded that like with realistic numbers, it can make it through, because the node is not very big, and the light can actually, it can jump over this node. And then we modeled other imperfections. So for example, of course, the sheath, this myelin sheath covering the axon, it's also not completely uniform. The cross-sectional area changes, and we modeled that. And it's also not, a nice circular thing, but it's like somehow funny shaped sometimes. So we modeled that. We always tried to quantify, how much imperfection can you tolerate. And in the end, we had a model, pretty optimistic conclusion. So it probably wouldn't work for all axons, but we think that there's a significant fraction for which it would. So high transmission for distances in the relevant range of millimeters to centimeters really seems possible, even maybe likely. Because the advantage is, the distances are relatively short, right? So we are not trying to go over kilometers as you can in optical fibers, but we are just trying to go from here to here or something. So that's good. Then we tried to estimate the rates. So they're based on these Chinese experiments with the brain slices. We came up with this has large uncertainties. Okay, so but maybe there's 1 billion photons emitted per second throughout the brain, something like that, order of magnitude. And that's not a lot. That's not something you would easily see, but it's fine for me. Okay, so from a quantum perspective, that's already a lot. You could transmit a lot of information that way. People in psychophysics, there's not as much work on this question as I would like, but people have tried to think about the bandwidth of conscious experience, like how many bits sort of are you really aware of? And the numbers are modest. Some people have very low numbers, other people a bit more, but it's the range like 100 to 100,000 or 1 million bits per second is probably what you really can experience. So I have more photons than that available, supposing that they play the role. Okay, so how can we know? How could we find out if that's really true? So there's actually a lot of things one could do, and they are all kind of hard, but I think they are not impossible. So for example, if one is interested in the guidance issue in particular, then you could try to isolate a living neuron, like with its axon intact, and couple light into it and see if light comes out the other end. And you might have to try a few, and it's not easy to have the same expertise, in the same lab of like keeping it alive and coupling the light and so on. But that's certainly something that is worth pursuing, I think. One could also, second point is one could try to prove the presence of these photons in the neural tissue. by injecting some light-sensitive chemical, and that should show that there are photons there. One could, again, if one is interested in the light guidance in particular, one could also introduce artificial sources, maybe in a living tissue, like nanoparticles, and maybe artificial detectors too, to be really sure, and just to study the light guidance. One could, if one is more interested in the photons per se, one can try to pinpoint, and that's something that's a colleague is actually trying to do, trying to pinpoint the sources of these biophotons more precisely. Okay, but it's early days in that too. And finally, also the opsins, one could try to see if these naturally occurring opsins that are not the ones in the retina, but the ones in our brain or elsewhere in our body, if they really can serve as light detectors. Because in the retina, there's a whole chain of like things that then translates the conformation change of the rhodopsin into an actual neural impulse. It's not clear that happens in the body, right? But one could try to see what happens. Do they really change the conformation? This is all very complicated, right? Unfortunately, but it would be worth doing. So here's something that I find encouraging from the point of view of the light guidance question. There were these experiments about 10 years ago on so-called Müller cells in the retina. People had been wondering for a while why the photoreceptors in the retina are at the back, sort of they are behind another layer of cells, and which are these Müller cells. And it seemed like the Müller cells were just in the way, kind of, and that was kind of odd, like why would evolution have done such an odd thing? And then people discovered finally that there's a really good reason. The Müller cells are actually light guides. And so they guide the light towards the photoreceptors. And what's nice for me and my story here is that the Müller cells are glia cells, which is exactly what the myelin sheath is made of. So I find that somehow compelling, that it could really be true, that the myelin also serves that purpose. There's also, more broadly on the question of light, there's a small number of papers that I've been able to find, but going back pretty far, like to the 80s here, on effects of small amounts of light on the brain. So cortical tissue can respond to low-intensity light in interesting ways, but there's not a lot of work on that. It seems like it might be true. Okay, fine. So this was the photon part of the story. Then if one really wanted to have quantum networks in the brain, one would probably still need a bit more, not just photons, but also some kind of more permanent sort of storage of and maybe processing capability of this quantum information. And to me, as a quantum engineer, that I would go with spins, definitely, at our current level of understanding, because spins can have good coherence times and they couple to light relatively naturally. And there are some examples in that context that are encouraging also. So in particular, magnetic field sensing, so magnetoreception, at least for birds, is one of the most popular theories for how that works. So it's not understood, but one of the most popular explanations involves spins. So it involves the interaction of photons and then electron and nuclear spins. It's called the radical pair theory of magnetoreception. And it even seems that quantum effects play a role. So very serious people now read papers with titles like this, The Quantum Needle of the Avian Magnetic Compass. And that talks about this interaction of photons, electrons, and nuclear spins in this hypothetical process. And that's exactly the ingredients I would use for a quantum network too. So, okay, for what it's worth. We are particularly interested in my group now in oxygen, singlet oxygen, because I mentioned that the reactive oxygen species are thought to be sources of biophotons. And on the other hand, oxygen has very interesting spin properties too that are somehow similar some of the properties of some systems that we use in quantum technology, like these NV centers in diamond, for example. So we are trying to pursue that. All right, so here are my conclusions. So I think there are really many reasons to wonder about the role of quantum physics in consciousness. I mentioned 3 main ones. One is the apparent role of the observer in quantum physics. Another one is the binding problem, the unity and complexity of consciousness, sort of simultaneous unity and complexity, where entanglement seems like a good fit. And then there's the idea that maybe nature is also using quantum computing. So 3 reasons that I think that's pretty good. Recent progress in quantum technology makes it much more believable, I think. That's also important. Then I said that spins and photons, to me, from my professional experience, seem like the most promising systems. If I had to build a distributed quantum processor, that's what I would use. Then I said that there are photons in the brain, and there seem to be detectors, so opsins. Then our main paper so far on this was really the one about the axons, so that the axons can plausibly act as waveguides. And the spin-photon interfaces, we really don't know, but we are working on that. So with that, I will just thank the people who have been involved in this, various collaborators, the people where I didn't put an affiliation, are the people from Calgary. So there's quite a few there. All right, thank you very much.
Thank you so much. Let me ask Lucien and Bob to come up for discussion. In the meantime, we'll take a couple questions for Christoph.
Thank you, Dr. Simon. It's very interesting research. I'm wondering, I don't know what the photon wavelengths of detection for these opsin sites are, but you talked about creating a network, kind of a linear network of receptors being, signals being passed through the axons. What about the possibility of them detecting really low frequency photons from outside the body? Is that a possibility with the way that these work?
I think
from other individuals or other sources.
Right, there is some light that leaks through the skull. I think that's true too. So that could also happen. Is that really what they are for? I don't know. I mean, it's more interesting, I think, if they are also used for internal communication. But of course, one shouldn't exclude that possibility. Yeah.
Thank you.
Over there.
Hi. So typically, when you have an animal or a human perceiving an object and they're having to do perceptual binding, you'll see oscillations that are synchronized between the 2 hemispheres of the cortex. But if you transect the corpus callosum connecting the 2 hemispheres, that synchrony across the cortex disappears. I was just wondering if entanglement is playing a role in that binding. Do you think that your approach could account for this observation in that effectively by severing those white matter tracks, you're basically severing the waveguide?
That would be great, yeah. Of course, it could be that you're just interrupting the electrical connections, right, too. But sure, I would really like that if that was true, yeah.
Thank you.
Split brain prep. All right, 2 more questions for Christoph, then we'll open it up.
Okay, is just a comment about the quotations. The first paper where people was talking of Bose condensation in brain in a quantum model has been in 1967 by Umezawa and Ricciardi, much before Marshall, who quotes that paper. And also talking about photons, apart biophotons you have mentioned, there is a paper by Carl Pribram, Kunio Yasue, and Mari Jibu in 1996, where they analyze all this photon business in the brain. Considering waveguides and as you are doing, yeah.
Okay, so
just for the correctness.
I'm always looking for historical references.
Yeah.
Because I think there's a lot more. Like I discovered the Marshall stuff only recently. So to me, what was new in his paper was the link to the binding problem. To specifically highlight that. But I don't know. Maybe even that is older because I feel like David Bohm could have thought of it. But I haven't seen any
No,
evidence that
but
he
in a
had.
very specific way, talking
Right.
about boson condensation and also about binding problem, that one also
So please
in my papers. Yes.
Send me the papers.
Okay.
Giuseppe, I'm a co-author on that paper. I'll tell him about it.
Yeah. No,
On that
but I mean, just for, you can quote whatever
about-
you want, but not say this is the first.
It's about ordered water inside microtubules generating superradiance and...
Exactly. I mean, thank you.
Hi, Dr. Simon. Hi, Dr. Simon. Thank you for the presentation. That was great. In your model of light propagation along the axon, I just wanted to know, was that a classical wave, or is it a single photon, or how does the intensity of the signal play into your model?
So the light guidance is really what we call a linear process, so it really doesn't matter. You know, you can guide a single photon, or you can guide macroscopic light. At some point, if you have too much light, other things will happen. But so it makes no real difference for the guidance.
Do the imperfections from, say, microtubules or opsins along the way make a difference if it's single versus a classical wave?
No, only if it's a lot of light.
Okay, thank you.
Just sit down. Okay. All right, so we'll open it up to all three speakers now.
Yeah, my question is more related to the fundamentals of quantum mechanics. Does quantum mechanics have the right foundations to study consciousness? You have pointed out two problems, the binding problem, the measurement problem, and one which you did not point out is the 0-point fluctuations, or the vacuum energy is 120 order of magnitude higher predicted from quantum mechanics than the actually observed in the universe, the cosmological constant. So all these three big issues behind quantum mechanics, don't they take the rug from under it to study consciousness, especially with regard to the universal consequences of the consciousness as non-locality?
To whom is that addressed? Or is that a statement?
To the panel itself.
So I think so one reason why quantum theory might be relevant is because it's the best theory we have, and brains are made out of matter, so it's the best theory we have to describe the brain. So in some sense, it has to be relevant at some level of description. Of course, we may in the future have a much deeper theory, a theory of quantum gravity, or even a theory that goes deeper than that, and then that would be the better theory to use to describe, to attempt to understand consciousness. I personally am not so impressed by the introduction of consciousness to solve the measurement problem. I don't personally see a route to understanding consciousness along those lines. So one thing in particular is that it seems to be a sort of a fairly passive way of introducing consciousness. If you just collapse the wave function, it's difficult to sort of alter facts in the world. I mean, you can do it. There's something called the quantum Zeno effect, where you can sort of drag a quantum state from one place to another, but I'm not sure that it's a very good way of changing things in the world. So I'm not terribly enamored of that way of using quantum foundations to understand consciousness, although that does seem to be the majority of the work that's been done is along those lines.
Maybe to add one thing. So I think the reason why I think that quantum physics might have something to offer, sort of in addition to the things I already said, is that it makes sort of matter much more interesting, right? Like matter from a classical physics perspective is very dead. You know, there's not a lot going on. Whereas with quantum physics, you immediately see that things are much more subtle. You know, there's these weird things like superposition, entanglement, even matter. You know, even if you don't talk about mind, matter, already information plays a role, right? So I find that inspiring to think that maybe quantum does have something to offer.
Yeah, I'd just like to give
we'll
one
see.
clue. One clue to those solutions is the solution, in my view, I just submitted a paper, lies in the fact that what is the source of quantum fluctuations? What is the source of photons and quantum particles? accelerating to the speed of light, and that study of that motion itself is the key to understanding the fundamentals of quantum mechanics, relativity, and consciousness. I'll just close with that comment.
Okay, thank you. I might make one comment in that practical application that if quantum optical processes are identified in the brain, see what anesthesia does to it, and see if it goes away reversibly. In fact, Travis Craddock has done something very similar along those lines. Over there, please.
Thank you.
Yeah, so my question is in regards to frequency. So I'm not sure how much of you guys are aware that infrared light is already used in neuroscience to stimulate individual cortical columns. If you can get a good optical window, you can use very small amounts of near-infrared light to stimulate neurons directly. So could you comment on that, and maybe on any ideas about where the wavelengths of these types of interactions might be happening?
I can answer that, I think.
Mike.
I don't need a mic. I'm toned up, I think. Do you hear me? Am I recorded? Anyway, when you say infrared light, you mean light in the near infrared and the short wavelength infrared, going from 800 nanometers to 2500 nanometers.
Yes.
In that region, there's water that dominates the spectrum. However, there are 4 windows called optical windows, which allows the light to go deeper. There's one window called number 3, which has been dubbed the golden window, and that is at 1700 nanometers. At 1700 nanometers, the light penetrates the deepest, and it eliminates most of the scattering. The problem why you don't see through the body is mainly due to scattering and water. And obviously water is the dominant feature. But there are these windows that you can penetrate through, and you can put your wavelength in those windows and do the Raman scattering at 1700. The reason why those windows have not been attacked by the community is because of silicon. Silicon dominated the field. That's your cell phones. That dominates the wavelengths from 400 to 900 nanometers. So the near-infrared has been dominated for years. Now there's new detectors that allows you to go into the near-infrared and short wavelength infrared. And I like this window number 1700, which I dubbed number 3, which is that you could go the deepest. Remember, scattering varies as 1 over lambda to the square. In the visible, it varies as 1 over lambda to the 4th power. So going into those windows eliminates scattering, which is the dominant feature why you can't see through your finger. Where's my pen? Do I have my pen? I do have my pen. Everybody has it. Every kid, you have that light point. Every kid loves to do, well, it didn't turn on. Can't even show you, my God. It died. Sorry. Sorry. Oh, there we go. I don't know if you can see that. Every kid does these things. They shouldn't do. That's about 700 nanometers, 680. So if you go into the infrared, scattering is reduced, goes deep into the material, and more Raman would be done in those regions to go deeper into the brain, for example. But again, there's only a limit to about 5 millimeters. I don't know if that answers your question, but that's what
Maybe I want to say something too. So I think you said stimulation, right? People are using it for stimulation. So what I would like to know, and what I don't know, is the intensity. Like, is it an effect where you can explain it with heating, right? So of course heating up the cells does a lot. Or is the level of light so low that it can't be heating? Then it would be very interesting to me. So I would be interested to learn more.
So my understanding of it is that it's subthermal. So
Okay.
it's not, heating is
Okay,
not
so
a
in that
component.
case, I'm very interested to hear more about it, actually.
Over here.
So this is for Dr. Simon, but the panel as a whole. Dr. Simon, you brought up entanglement and non-locality as an approach to the binding problem and unity of consciousness, which seems really very promising. And I'd like to hear your thoughts about it. And is there any experimental avenues that you can think of to approach it?
Right, so as I said, that this is not my idea, right? This has been around. Certainly Marshall already articulated it 30 years ago. Is there a sort of direct way? So I don't know. It's an interesting question. So like the things the experiments I was describing were all at the sort of microscopic level, right? Trying to see if these quantum things, if the light really goes through, or does it play a role, and things like that. Could you attack it from on a more macroscopic? I don't know.
Now, could you show entangled photons in wide-ranging regions of the brain in principle?
Right. I mean, if they are guided, you could start playing games where you like send entangled photons in, and like, so there's many elements, right? Like you would want to understand the sources, you want to understand the detectors, you want to see if there's some interface with spins or something like that. So there's many things one could try for sure. Yeah, I'm hoping that people will pursue all these different avenues. Like Robert, he's sending entangled light through brain tissue already. So that's a little step.
The first step we did, the first step is going through the brain tissue and seeing classical beams, which we call, some of them are classically entangled. We use one beam, essentially you can't tell till you measure them locally. Then there's the quantum entangled beams, which we're going through tissues for the first time and seeing still there's a correlation. It's just the start.
Yeah. There's maybe a really different thing one could try, which is to see to what extent to come at it from the psychology perspective, actually. How good a match is there really, mathematically, between the properties of consciousness and the properties of entanglement? There is actually a field that's called quantum cognition, where people are doing this for their own reasons. You know, they are looking at this analogy, and I think it would be interesting to pursue that more and see if there's really a good mapping between these two things. Yeah.
The next experiment we're doing is on live mice, is to look at the brain on these entangled beams on a mouse that is alive instead of just tissues that are, and then following along Stu's idea is to put them under anesthesia. But we want to do reflection off the mice because we're not going to be able to go through and do transmission. So we have to work on reflecting the optical beams off the brain. Instead of going, the easiest beam is to go straight through.
I just may mention one other issue that's related to all of this. Presumably, if entanglement has to do with unity of consciousness, one wants to entangle some preferred set of whatever, say neurons, that can change in some way for different circumstances, and how to address a specific set of neurons and entangle them, or quantum variables and entangle them, needs to be thought about.
Right. Correct.
Yeah, this is for, I guess, Mr. Simon, or Dr. Simon. You mentioned the waveguide properties of basically the glial cells, and there's been a considerable realization that those cells play a much larger role in the brain than we've thought of in the past. One of the difficulties has been that they're coordinated by calcium waves, which are quite slow. Is it possible that these waveguides that you mentioned in axons could be more global and therefore provide a very rapid communication network for those cells?
It sounds like it, yeah, maybe. So. I want to be cautious, right? But certainly the glia cells are very interesting because of their refractive index. Yeah. So from a light guidance perspective, I think one can say that this work on the Müller cells proves that glia cells really are good for light guidance. So, yeah.
Thank you.
So I have a big picture question for all the panelists. Carl Jung studied meaningful coincidences, which he dubbed synchronicity, and worked with Wolfgang Pauli on the theory and thought that it might be evidence for large-scale entanglement outside the brain. I think that I feel like there's a lot going on at this conference, actually. So, but I'm curious what you guys think of that. If it's just if it's a real phenomenon, or if there's reasonable quantum explanations for it?
I mean, I suppose for something, for quantum theory to play a role of that sort, you'd have to imagine quantum effects being between different brains. And so it's difficult to see how quantum entanglement would precipitate between two people without the sort of messy environment decohering it. If that were possible, then you could have the kind of effects I mentioned earlier, where people don't have to communicate as much as they would in a classical world to evaluate functions. And so that's something that would be mathematically possible, although physically I don't see it would be. I like the idea of Jungian synchronicities, but I don't see how to support them at this stage in a sort of quantum framework. No.
We have about 8 more minutes. I'm going to take the chairman's prerogative and ask Roger to cut to the front to ask a question, if you guys don't mind, please.
Sorry, I had no intention to queue jump. It's only just that various people mentioned, well, the Wigner point of view and so on, that consciousness reduces the state, and not really explicitly the opposite point of view, which Stuart and I adopt, which is that the reduction of the state involves a change in quantum mechanics. So we're looking not at standard quantum mechanics, but some modification of it, which we believe is needed, and that the reduction of the state takes place in the world, and that's what consciousness is about. And I was a little surprised. I don't think that Lucien mentioned that, although it was in one of his pictures he had these speckles of whatever they were, and maybe that was the viewpoint. But I just wondered what Lucien's viewpoint on this was, because it wasn't really mentioned explicitly, and perhaps the other panelists might have a comment to make. Clearly it's needed from our perspective that you have quantum mechanics playing an important role in the brain activity, otherwise you'd never get to the level where it's the violation of quantum mechanics that have any effect at all. So it's clear that things like this demonstration that quantum mechanics is playing a role in many ways in brain activity, but it doesn't address the question that we're really concerned with here about how consciousness comes about. So I just wondered whether the people in the panel had anything to say about this point of view, since it didn't seem to be mentioned explicitly as far as I could make out.
Yeah, so I guess the kind of violation of quantum theory I was talking about it isn't that kind of violation. And one could ask whether collapse is actually a violation of quantum theory or not. It's certainly a violation of unitary quantum theory. But you can describe, in the sort of framework sort of operational quantum theory, you can describe collapses, in a mathematical way, and it doesn't take you. It takes you outside of unitary quantum theory, but it doesn't take you outside this broader framework of operational quantum theory. And in fact, there you even have a sort of continuum of processes, ones which induce very strong collapse on the one hand, and ones which are unitary on the other hand, and then you have stuff in between. Sort of completely positive operators are the more general concept, and so you have a continuum from strong projective measurements to unitary evolution. So the sort of violation of quantum theory I was talking about here, I think, is a much stronger violation, because you would see Bell correlations no longer being present, and that would have to speak to a different kind of theory. In fact, it would be a superdeterministic theory, so it wouldn't look, it wouldn't be a probabilistic calculus at the deep level like quantum theory is. In terms of quantum theory providing an explanation for consciousness, I mean, you of course have done a lot of work in relating it to things like insight, and maybe these processes can be non-computable. I still find it hard to bridge to make the bridge from that to solving the hard problem of consciousness. David Chalmers has talked about. But of course, there may be some way to do that. It's difficult to say.
I'm going to talk about that tomorrow. But what he's proposing solves the measurement problem. You don't have a solution to the measurement problem, or do you?
Yeah, I wasn't trying to propose a solution to the measurement problem, because if the sort of thing I was talking about was seen, then you would have to have some sort of superdeterminism, and then it would be we would have to be in an entirely different theoretical framework. We'd know that quantum theory was only a statistical sort of theory, not the deep fundamental theory. Something more like the de Broglie-Bohm model would have to be true, but you'd have to it would have to be modified to make it consistent with what I was saying. Of course, this is a long shot. It's very unlikely that we'd see the results I was suggesting.
Did you want?
Yeah, so just to be clear, my list was not at all intended to be exhaustive, right? So of course I know your work very well, and I was assuming that many people here probably know it too. So I'm very happy to add that to the list as a possible, as an additional motivation. Yeah, I was also not trying to, I think I was really focused on the problem of consciousness and how could quantum be related to that. Of course, if the solution moreover solves the measurement problem too, that would be great, but I would already be happy if it didn't also. Yeah. So.
Thank you.
This question is mostly just for Dr. Hardy. Unfortunately, I was not able to make it to most of your beginning presentation. I was curious why you chose to use EEG as your form of measurement in your experiment rather than fMRI or anything else, and specifically is it because you think there may be interference with the results?
I mean, anything which is quick, so you get the signal out quickly and cheap, because you need to use these apparatuses on enough people to get a strong signal. And maybe there's a trade-off there. Perhaps MEG you would get a stronger signal from an individual person, but I assume it's more expensive to put a MEG apparatus on somebody than an EEG apparatus. But of course, I'm not an expert in these kinds of fields, so I would have to learn from the experts there. So anything where you get the signal out from the brain very quickly, so that the information hasn't sort of traveled several times the radius of the Earth, would work.
Thank you.
Okay, we're running out of time, so let's have just one more question, please.
Thanks. For Lucien Hardy, for the layman, could you explain how only humans show a broken quantum correlation? Maybe we can narrow it to the example you gave, if you could just clarify it.
Right. So the conjecture, and it's a long shot, but the conjecture is that if there was some sort of mind-matter duality, and yet the world was fundamentally local, then systems like humans, perhaps also penguins, as I mentioned, would have this sort of mind acting on matter, and so they would be able to change the setting in a way that couldn't be anticipated by the physics happening at the other end of the experiment. And under those circumstances, you would expect to see a result. You'd expect to see quantum theory violated. But it is a long shot. It would.
Thanks.
Yeah.
Okay.
Okay. Let's thank our speakers for a great session, and the audience for hanging in there for good questions. And